Well, now for part 2 in our mini-series on partial fraction decomposition. I've written the integral at the top, and that's the one we will evaluate in this video. It's the integral of 2x over x minus 2 in parentheses times x plus 1 in parentheses squared. Now, what differentiates this from the last example that we had is that in the denominator, we have a squared factor, meaning we have the same factor being multiplied by itself twice. And I've written 3 possibilities for the correct form of the partial fraction decomposition. The first in orange, the second in pink, and then the last in red. And I want to invite you to pause the video and to think for a moment about which one of these forms is going to be the correct form for our partial fraction decomposition. And I'll give you a few moments to think about that before we move on. Well, all right, if you chose the last one, the red one, then you're correct. And if that surprises you, you're probably not alone. But let's look at all 3 of these ones, and we'll start with the orange one, the first one, and we're going to look at why the first 2 are wrong and why the third one is probably correct. So if we rewrite the first one, and I'll say, okay, a over x minus 2, and this makes sense because I see an x minus 2 in the function here. So then plus, well, a b over, well, I see an x plus 1 squared, so I assume that's x plus 1 times x plus 1. So following the form of partial fraction decomposition that we learned in the last video, I would presume that this would be an x plus 1, and that I would then repeat it. Well, if we look at this, we can actually simplify this a little bit. We can combine the 2 last terms, so then we would get a over x minus 2, and this would be plus, well, b plus c over x plus 1. And what has happened here is very quickly our b plus c is just equal to some other constant, and I will say that is d, so I'll actually erase that and I will write d here. One of our factors has just disappeared. We started with 3 factors up here in our original function, and now if we write it in this form, the first form, well, then we can combine the 2, and one of those factors disappeared, and that's not what we want because obviously we have 3 factors. So pretty quickly we can decide that the first example is probably erroneous. If we look at the second example, it's not as obvious why that would be wrong, but we can try to solve it as if it were correct, and then we'll see what happens. So we will grab the same color here, and we will say, okay, well, assuming this is correct, if we multiply both sides of this equation by the denominator of the first, which is x minus 2 in parentheses times x plus 1 in parentheses squared, then what we'll get is we'll get 2x is equal to, well, the x minus 2 will cancel, and the x plus 1 squared will stay, so that's times a, and then plus, well, the x plus 1 squared will cancel, and we get an x minus 2, and that'll be times b. Well, what happens now when we distribute everything? We'll get a 2x, and this will be equal to, well, an a times x squared plus 2x plus 1 plus b times x minus 2, and now if we distribute everything, we get ax squared plus 2ax plus a plus bx minus 2b. Now we will, following the convention here, well, we can rewrite the left-hand side, and we can say, well, this is actually equal to 0 times x squared, right? That would just cancel out, plus 2x plus, well, that's plus 0, and this is equal to a times x squared plus, well, we can combine the x terms here, and we get a 2a plus b times x, and then plus a minus 2b. Well, if these 2 sides are equal, then it would make sense that the coefficient of the x squared equaled the coefficient of the x squared, and that the coefficient of the x equaled the coefficient of the x, and that lastly the constants on the end equaled each other. So we would get a linear equation here, and we would say, okay, well, we know that our a is equal to 0, and that our 2a plus b is equal to 2. And we know that our a minus 2b would equal 0. Well, if this is the case, well, we know that our a is equal to 0, which means, so if we plug it into the second equation, then what we would get is we would get 0 plus b equals 2, so then b equals 2. And if we check these in the last equation, we would get 0 for a minus 2 times 2 for b is equal to 0. And we would get negative 4 is equal to 0. And we know that is not true. So when we try to write, or rather try to decompose our fraction in this form, we find that it leads to an erroneous result. So we are left with our last condition here. And this might look strange to you, because it might look like we are decomposing it into 4 terms because we have the x squared there, which looks like 2 terms. But in reality, if I can try to make some intuitive explanation here, what we're doing is, well, we actually could decompose this in terms of the second way here, but we would have to modify it a little bit. We would have to say, okay, well, this is x minus 2, and then this is plus, well, not b over x plus 1 squared, but rather we could write it as bx plus c over x plus 1 squared. If then we tried to solve this, it would end up working. But then what we would end up getting is we would end up having to separate this, because this wouldn't necessarily be fully decomposed. We would still have an x in the numerator, and that's what we're trying to get rid of. And then the only way that we would be able to separate this is then if we separated this into two more fractions, which would then have the form of this. And that is essentially what we have right here. And then if we added that to our a over x minus 2, we would have this third form. Well, we're going to look at an example, and hopefully that will help this make more sense to you. But in general, whenever you have some sort of repeated term in your denominator of your function that you're going to use a partial fraction to decompose, what you will do is if that term is over the power of, let's say, so this is x minus a to the nth power, right? And we will say that this is, we'll just say that we have some sort of constant above this. So let's just say this is b. What this will be decomposed into is this will equal some other constant, and I'll say b1, and this is going to be over x minus a to the first power. And then we will add that to, well, it will be some other constant, so b2 over, well, this will be x minus a to the second power. And we will keep on doing this on and on and on until we get b to the n over x minus a to the nth power. So in the case, and if we had something over x, and this is something over x minus, let's say, 1 cubed, what we would do is we would end up having something over x minus 1 to the first power plus something over x minus 1 squared plus something over x minus 1 cubed. And that's the form that we follow. in the above example, we followed that only up to the second power because that is the power that was in our original function. So now, lastly, let's solve the integral. Let's decompose it and then solve it in the correct manner. So I'll rewrite it. We have the integral, and that is of 2x over, that's over x minus 2 and x plus 1 squared dx. Just making sure that's all correct. Yep. Okay. So we know that 2x over x minus 2 times x plus 1 squared is equal to, well, a over x minus 2 plus, this will be b over x plus 1, our first repeated term here, plus c over x plus 1 squared. Well, now if we multiply both sides by the denominator of the left-hand side, what we get is 2x is equal to x plus 1 squared, I'll write the a out front, plus b times x minus 2, x plus 1, and then plus c times x minus 2. Now, if we choose x to equal -1, then on the left-hand side we'll get -2 is equal to, well, the a term will cancel out and the b term will cancel out, and we'll say, well, c times -3, which means that c is equal to 2/3. Now if we say that x equals 2, then we'll get 4 is equal to a times 3 squared, which is 9. The b term will cancel out, the c term will cancel out, and we'll get a is equal to 4 over 9. Now, unfortunately, there's no values that we'd be able to plug in to solve for the b, but we can plug in the c and the a, and we can choose some convenient value of x. So let's say that x equals 0, and we'll say we'll bring our values of a and c down, and if we plug those in, we'll be able to solve for b. So if x equals 0, the left-hand side equals 0, that's equal to 4 over 9 times 1 squared plus b times -2 times 1 plus 2/3 times -2. So 0 is equal to 4 over 9 minus 2b minus 4 over 3. Well, that means that 2b is equal to 4 over 9 minus, well, this is equal to 12 over 9. So b is equal to 1/2 times, and that would be a 4 minus 12 is -8 over 9, which equals minus 4 over 9. So we solve for our a, our c, and our b. Now we can rewrite our integral. So we know that this would be the integral now of well, our a term would be first, and that would be 4 over 9 times 1 over x minus 2 dx plus, well, our next one was minus 4 over 9, so it'd actually be a negative here. So minus 4 over 9 integral of 1 over x plus 1 dx, and then for our last term we'll have plus 2 over 3 integral of 1 over x plus 1 squared dx. Now quickly solving these integrals, we get, well, this will be the ln, the natural logarithm, the absolute value of x minus 2 minus 4 over 9 times the natural logarithm of x plus 1. Now be careful here, this isn't the natural logarithm. This is the same thing as x plus 1 to the minus 2. So if we were to integrate this, well, then we would have to add a power and then divide by it. So then that would be minus 2/3 of x plus 1 to the minus 1 plus c. And if we just check this last term, if we were to take the derivative of this, we would bring the -1 down. That would be a plus 2/3 x plus 1, and then we would subtract 1, that'd be a -2. Yes, that's the same thing. So we know we did that integral correctly. And now we have our answer. 4/9 ln absolute value of x minus 2 minus 4/9 ln absolute value of x plus 1 minus 2/3 times x plus 1 to the minus 1 plus c. And that is how we solve integrals, how we decompose the rational functions that have repeated factors in the denominator. I hope you enjoyed. I hope you found this video helpful. If you have any questions, leave a comment below, and I will see you in the next video.